and it's just missing one of them. In essence, I only would need one polynomial. I mean, only one polynomial coefficient is unknown to me. Let's say.
Yes, but even if
I could still search. I mean, so that means, in other words, the number of unknowns is much less than if I say it is missing 2. If I just need to know A1, it's a lot smaller than even know A2. So don't I do some security?
No, because we work in a finite field. So the modulo prime Q is there. So even if you know K minus 1 number of shares.
Right, but the AI, of course, is in a finite field as well, right? So I want to do a brute force search to generate all possible AIs. If I was only missing one coefficient AI, I could just basically search over the whole size of the finite field. If I was missing 2, I could search over 2. So then in terms of brute force attack, aren't I less secure if I'm only missing 1 share as opposed to if I'm missing n shares?
No, that's the beauty of the scheme. You know, even if you have K minus 1 number of shares, still even if you apply brute force method, you have to search the whole of the finite field, which is Q number of possibility. So then the thing is, even if you do not have K minus 1 number of shares, still you can use the brute force method, right? So those information of the K minus 1 number of shares are useless.
How big is your finite field?
It depends on the Q.
What's Q do you use in your research?
So in image, Q is 251.
Generally, so if you had a large enough machine, you could actually reconstruct it if you had K minus 1 shares, right? If I was willing to spend the time or bring the computation, I think that's the question. I could check with each one to see which reconstructs it.
So that's what I'm saying. Even if even if you have K minus 1 number of shares, information about K minus 1 number of shares, that is equal to the information even if you do not have any information. For example, you consider the case where you have no information about the share. Still, you can use the brute force method. You can source the the Q number of possibility.
But you said it's 251 possibilities?
Sorry?
You said it's only 251 possibilities?
Yes.
That's a really small number, right?
Yes.
So it's not very secure at all.
But that's the image. So it's not only one secret. So we have number of pixels. So then the possibility is 251 equals 251.
We're using a different Q and a different AI for each pixel?
Yes. So we operate on the pixel level.
But you're using the same code for each pixel, right? The same AIs for each pixel?
Well, we can use, but we don't use that. We use different pixels, different AIs for different pixels.
Okay.
So that's why this scheme is called perfect secure scheme. What perfect secure is, even if you have K minus 1 information about K minus 1 shares, that's equal to the information you do not have any information.
So what information does are the AIs known to are the AIs public or are the AIs secret?
No, the AIs are secret.
So how does somebody decode when they get in shares?
Sorry?
How do you decode when you get in shares? Don't you need the AIs?
How I decrypt it?
Yes.
So those information about those AIs are hidden in the shares. So using this K number of shares, I can find the polynomial. Then once I know the polynomial, then I can know the AIs.
How's that done?
By Lagrangian population. That's how it's done.
Okay, sorry, go ahead. Oh, right, okay.
So yeah, that's the summary situation. Any other questions? Summary situation?
Okay, so can you just go back one slide? Oh, sorry, and one more slide. So the share is the share is what here in this formula. Do you mention is the share here already or not?
Yeah, share is the here x is the variable in this formula. So if you want first share, put x equal to 1. If you want second share, put x equal to 2.
Okay, so it's like 78 points of the polynomial.
Shall I move to my original slides?
I guess my fundamental question is, with this scheme, is the search space smaller if I have n-1 shares than if I have just 0 shares? If I were to do a brute force search.
Yeah, so yeah, even if you have information about n-1 shares, it's equal to information about 0 shares. So k-1 shares is equal to information about 0 shares.
I still don't understand why that's the case.
Can you just sketch a proof for that?
Yeah,
Yeah, sure.
use the board.
Yeah, sure. Where is the... So let's 6 is the secret, and 7 is the prime number, and we have 2, 3 secret sharing, where I use 6 plus, and I use A1 equal to 5x. Not 2. Not 7. So this is my fx. I find f1 equal to 6 plus 5, 7, 4. And so. And f2 equal to 10, 6, 7, 4, 2. Right. Now I have no shares, but I know the prime number as q equal to 7. So I have to know the secret. I have to sort 0 to 6, right? So I have 7 possibility. So the probability of knowing is 1 by 7. Now suppose I have 1 share. So I know 4. Now, by knowing 4, I know that 4 is in, for the 6, from 4 I have to know 6, right? So, even I have 4, still, and I have 0 to 6, the prime number range. So I choose, let's say, 0. First let's say I consider that 0 may be the secret. Then this 4 and 0, let's say, map to 4. What I am trying to say is for 4, for different value of 0 to 6, we can find different secrets here. Even if you consider, let's say, 0 is the case, you will find 4. 1 is the case, you will find 4 plus 1 is 5. 2 is the case, you will find 6. 3 is the case, you will find 0. And 4 is the case, you will find 1. 5 is the case, you will find 2. And 6 is the case, you will find 3. So even if you have the information about 4, still your sort space is 0 to 6. Because even if you know 4, still using 4 you can find different values. And these values can, even if you find it, I mean, this value you can infer even if you know information about 4. So, even though you have information about 4, that is not useful. That's what I'm saying.
So the AI is generated locally at the, where are the AIs generated?
So,
The AIs, where are they created?
AIs are generated by the server. So,
Okay.
so the whoever wants to hide the information.
Okay.
So he generates the AI, creates those shares, then destroys those that secret.
Okay.
And those shares are distributed. One share is sent to one data center, another share is sent to another data center. So that's what I'm saying. Even if k minus 1 number of data centers collaborate, still they cannot know the secret.
I think, I mean, the key really is that you're trying to fit a line or a parabola or an nth order polynomial. And you
Yeah.
can't fit the nth order polynomial until you have 2 points per line, 3 points, right?
Yeah, that's right. That's right. That's in fact another secret sharing scheme, bulky secret sharing scheme. But that's
You can't create a polynomial till you have all n constants or coefficients. But that doesn't stop you from doing what Doug is saying, that if I have the 5 coefficients, I could potentially fit some polynomial to those 5 coefficients of the order that you want, but it may or may not be the right polynomial. Okay, so that's, I think, the simpler answer.
Yeah, I think the easiest way to say it is there's a bijection between the last possible share and the secret. And so there's no information theoretic information. You're gaining no information theoretic advantage from having n minus functions. Or k minus functions.
You won't be able to be sure,
Right.
and that's...
Well, the thing is though,
That's
it's
more-
with images you can just look at them, right?
You may be lucky, but you know, since there are many such polynomials, you don't know whether you have the right one.
Well,
But actually,
with
no, no,
images you can do that. But if you do different polynomial for every pixel, then it's different.
Right, it's a different polynomial for
Right. Yeah. In that case,
So-
then it's not going to work. Yeah. All right. Thanks. Yeah, that was helpful for me anyway.
So any other questions? Maybe I will move. Well, so we address this, you know, we use summation, to go back to my original slides. We use summation secret sharing by secure multiplied computation scheme, and we address the incompatibility of the floating point number with summation secret sharing by excluding the modular prime operation from summation secret sharing or by converting the floating point number to fixed point number. Then, using the solutions, we propose 3 cloud-based secure image processing frameworks for 3 commonly used image processing algorithms. The first one is for image scaling cropping. So we call it our framework a secure cloud-based image scaling cropping framework. So the objective here is store those images in the cloud data centers and allow store those images in the cloud data center by adding those informations, and allows image scaling and cropping operation on the hidden domain.
So the data is stored encrypted as it's stored, or data stored unencrypted, or is data stored encrypted?
I mean, the server.
Does the server store the data images encrypted or not encrypted?
Yeah, encrypt. I mean, server encrypts those. Images, then send it to the data center.
But like on the hard disk drive or whatever, is it stored encrypted or not encrypted?
That's encrypted.
Okay.
So encrypted by summation secret sharing, using summation secret sharing.
By what?
Using summation secret sharing.
Okay. I got it. Okay.
Does this mean, by the way, that you're not doing any kind of you're not doing any kind of compression?
Currently, it's on compressed domain, but yeah, that's my future work.
Generally, in medical images is not allowed anyway.
But anyway, this is the first research in this area, so yeah, more research has to be done. So for that we need a secret image sharing scheme. So the secret image sharing scheme are the schemes where semi-secret sharing is being used to secret share those color of the pixel values such that those shared images, so the images which are found from the shared color values, they reveal nothing about the secret image. So semi-secret sharing has been used to secret image sharing schemes.
So is your idea that the different shares are stored on different, say, disk drives or in different cloud servers?
No, secret image sharing scheme is, we have an image, let's say x cross y number of pixels, and each pixel has the colors, right? RGB values. So we use semi-secret sharing for each color of each pixel. So for color of each pixel we use first semi-secret sharing, then we get the shares. From the one color we get n number of shares, right?
Right.
So for the second pixel also we repeat the process. So we get another n number of shares.
I'm wondering about where the data is stored on your cloud server.
Yeah, then the secret images, the share images are being stored in the cloud.
So you're showing like K shares
Yes.
on different servers on the cloud or all on the same server?
No, different servers.
Okay, so in other words, one has to access multiple servers to
Yeah.
get decrypt. Okay.
Yes. So for that we need a new secret image sharing scheme because the downside of using semi-secret sharing is the data overhead is very high. So for that, the existing schemes they use the RGB values like the red, green, and blue values of one pixel in one secret sharing polynomial. So they do not use any random number. So by doing that, they reveal some information about the image. Now to hide those information, they use another crypto system. That crypto system breaks the homomorphic property of semi-secret sharing. Now to avoid that, we use one random number, even if we have little more data overhead. And we propose a new secret image sharing scheme. And using this new secret image sharing scheme to share the images, we now propose our framework where we have the server, we have n number of data centers, and we have the client. And the server can be the hospital. And we assume that those data centers, no more than k minus 1 number of data centers can interact with each other at any point of time, or an adversary cannot access more than k minus 1 data centers at any point of time. If that happens, then our scheme breaks. Now the server, which is the hospital, creates n number of share images from the secret image, then sends each share image to the data center, distributes n number of share images among n number of data centers. And now each data center has the share image of the secret. So none of the data center can know the secret image knowing the share image. Now at a later point of time, the user requires scaling and dropping operations for each data center parallelly. And those data centers they perform scaling and dropping parallelly according to the user's requirement and sends the scaled and dropped image to the data to the user. After receiving at least k number of scaled dropped share images, the user recovers the secret image by using secret reconstruction through Lagrange invocation, and then displays the image. So we experimented a scheme using simulation. We simulated the server, data centers, and user in a PC. We didn't use the data centers or real cloud data centers. And we used 3, 4, 5 secret image sharing scheme.
So what does it mean you simulated? Why couldn't you just implement this?
Sorry?
I don't understand. What does it mean, simulated?
Simulate means we assume that the PC is a data center and the PC is the client and the PC is the server.
So you actually implemented this scheme?
Yeah. Yes. And
With a real image?
sorry?
With an image that,
Yeah. So we implemented this secret image sharing scheme using C. We implemented from scratch.
You actually implemented like the servers, clients and servers on the same PC, or just?
Yes.
Okay.
Because we found that even if we kind of assume that there is an PC, our scheme has, it doesn't have to do our scheme. That can be easily applied in the real system.
there's nothing to do with the cloud, so to speak. Right?
Yeah, that's right.
But you did implement the cloud protocol on one PC, right? Or you did not?
No, there's